Alright, so last time we looked at some of the topics leading up to cartan subalgebras. Today we are looking at a cartan subalgebra, which they abbreviate as cartan subalgebra. A cartan subalgebra of a Lie algebra L is a nilpotent subalgebra which equals its own normalizer in L. In L, so we don't guarantee this doesn't guarantee existence, and it seems that it's the way they write it means I think it's still open if it always exists in finite over finite fields, but if L is semi-simple and over a field of characteristics 0, then a maximal toral subalgebra H is abelian, and hence nilpotent. And then the normalizer in L of H is H. As L, we can split L into H plus the sum of the root spaces with the bracket of H and HL alpha being equal to L alpha. So we do have toral subalgebras in this case. Geez. And we can show our theorem here. We can let H be a subalgebra of L. Then H is a cartan subalgebra if and only if H is a minimal angle subalgebra. Let's look at the proof. Suppose that H is our cartan algebra. It's an angle algebra, sorry. L0 of the adjoint of some Z is an angle. Then it is self-normalizing. We've already seen that. If, in addition, H properly is minimal, it properly contains no other cartan angle subalgebra, and then by our previous lemma, the first of the two that we ended off last video with, we have that H is L0 adjoint Z inside of L0 adjoint X for all X in H. With the H adjoint of X nilpotent then therefore, by Engel's theorem, H is nilpotent. Conversely, let H be a cartan subalgebra of L. Since H is nilpotent, it is inside of each adjoint X. Assume H is not equal to L0 adjoint X for all X in H. Essentially, it's not equal to any Engel subalgebra. We can take L0 of adjoint Z for Z in H to be as small as possible. Then, by our previous lemma again, L0 of the adjoint of X is inside and contains L0 of the adjoint of Z for all X in H. Thus, in the representation of H induced on the non-zero vector space L0 of the adjoint of Z over H, each X in H acts as a nilpotent endomorphism, which means H annihilates some non-zero y in H, y plus H, so there exists y not in H such that H bracket y is within H. So H is not self-normalizing. Self-normalizing. And this comes with a corollary. Let L be semisimple with characteristic over a field of characteristic 0. Then the cartan subalgebras of L are exactly the maximal toral subalgebras. We've already done that every cartan subalgebra is a maximal toral subalgebra. Or no, we did that every maximal toral subalgebra is a cartan subalgebra. So we're going to let H be a cartan subalgebra. And for the Jordan decomposition of X into the sum of a semisimple and nilpotent component, then we have that the L0 of the adjoint of XS is within the L0 of the adjoint of X. As any Y killed by a power of the adjoint of the semi-simple component of x is killed by a power of the adjoint of x, since the adjoint of the nilpotent part of x is, well, obviously going to be nilpotent, and will commutes, we saw by definition, with the adjoint of the semi-simple. Note that for semi-simple x in our L, that L0 of the adjoint of x is the L centralizer of x, with the adjoint of x being diagonalizable. Now the cartan subalgebra H is minimal. Angle as of the form L0 of the adjoint of x. And then we have that H is L0 of the adjoint of x is semi-simple, which gives us the L centralizer of access, which must, this last centralizer here must include a maximal toral subalgebra of L, which is itself a cartan subalgebra hence is a minimal angle hence H as a whole must be a maximal toral subalgebra. And we note that this means a maximal toral subalgebra of a semi-simple Lie algebra over a field of characteristic 0 must have the form consisting of the centralizer in L of S for some semi-simple element S. Such an S is called regular semi-simple. Regular simple. Let's look at what they call functorial properties. Which consists of two lemmas here. First off, let phi from a Lie algebra to a second Lie algebra be an epimorphism. Which I believe means it's, in this context, mono is injective, this is going to be surjective. or close. Because I know in the category theory sense, apomorphisms don't have to be actually surjective, they just need to like cover all of the structure essentially of L prime, but don't worry about that. If H is a cartan subalgebra of L, then its image is a cartan subalgebra of L prime. First, we note that the image of H is nilpotent. We're going to let A be the kernel of phi, and we're going to identify our image L prime with L over A. If some x plus A normalizes H plus A, then X is in the L normalizer of H plus A. But H plus A includes a cartan subalgebra, which is a minimal angle subalgebra. So the subalgebra H plus A we know is self-normalizing. So X lies within H plus A, making phi of H self-normalizing. And there's a second lemma. Which we start at the same. We have phi be an epimorphism of the algebras. Let H prime be a cartan subalgebra of L prime, and we're going to let K be the pre-image under phi of H prime. Then any cartan subalgebra H of K is a cartan subalgebra of L. The proof: well, we know H is nilpotent. So by the previous result, phi of H is a cartan subalgebra of phi of K, which is definitionally equal to H prime. So because the cartan subalgebras are minimal angle, phi of H itself must be H prime. So if some element X in L normalizes H, then phi of X normalizes phi of H, so phi of X lies within phi of H. So X is contained within H plus kernel of phi. As we know by construction that the kernel of phi lies within K, X must then lie within, be an element of H plus K, which is going to lie within K. Since H is a cartan subalgebra of K, x lies within the normalizer of h, which is h. And we're done. Alright, things are happening. We're kind of always starting a new chapter in these videos. I don't know about it. It's not great, but we will be doing that again here. We're going to start our discussion of conjugacy theorem. This is our next chapter. So again, we're going to assume F is algebraically closed and character is 0. We're going to show that we will show that in an Lie algebra, arbitrary Lie algebra, all cartan, we will show in a Lie algebra L over F, all cartan subalgebras are conjugate under the group of inner automorphisms. For semi-simple L, this means all maximal toral subalgebras are conjugate. So L is going to be uniquely determined, as we discussed before, up to isomorphism by its root system relative to any maximal toral subalgebra. Because if you recall last time, we showed that the pairing of a semi-simple Lie algebra and a maximal toral subalgebra is uniquely determined by the root system. Now what we're trying to show is that our the maximal toral subalgebra that we pick doesn't actually change anything of isomorphism. So essentially we have a one-to-one relation between semi-simple Lie algebras and root systems. We will also show, as a step along the way, I guess, that all maximal solvable subalgebras of our Lie algebra L are conjugate. Our first section in this chapter is then the group. On rate like this, E of L looks kind of like the Mr. Saturn font, but they write it fancy. It's hard to write E. It's not a letter which writes fancy well, I think. So we're going to pick L. We're going to let L be a Lie algebra. We're going to call an element in L strongly nilpotent. Strongly adjoint nilpotent. If there exists some element y in L and an eigenvalue A of the adjoint of y such that x lies within L A of the adjoint of y. This, which of course means that x has to be adjoint nilpotent for this to work. To note by fancy n of L the set of all strongly adjoint nilpotent elements of L, and denote by E of L the subgroup of the interior automorphisms of the inner automorphisms of L generated by the adjoints of X for X in being strongly adjoint nilpotent. And as our NL generating is stable under the automorphisms, we get that our E of L is a normal subgroup is normal in the automorphisms of L. And we will see, I think we will see that when L is semi-simple, E of L is actually equal to the inner automorphisms of L. So we set this up to have like stronger properties, like if K is a subalgebra of L, then the n of K must lie within the n of L, strongly adjoint nilpotent elements of L. So we can define the subgroup goofy E of L on K of our goofy E of L generated by all of the exponential maps of the L adjoints of X for X being a strongly nilpotent element of K. Then epsilon K is the restriction of epsilon L semicolon K to K. By contrast, for X in K with nilpotent adjoint in X, we have no, oh, there's a bird outside. We have no guarantee on the properties of the L adjoint of X, and so no relation between the inner automorphisms of K and the inner automorphisms of L. Well, okay. So we see now if phi from L to L prime is an epimorphism and Y is an L, then phi of LA of the adjoint of y is LA prime of the adjoint of phi of y, giving us that phi of the strongly adjoint nilpotent elements of L are the strongly nilpotent elements of L prime. This brings us a lemma. Let a map phi from L to L prime be an epimorphism. If sigma prime is an element of goofy E of L prime, and there exists a sigma in goofy E of L such that, and then there's a diagram. We have phi sending L to L prime, and we have sigma sending L to L, and sigma prime sending L prime to L prime, and this diagram has to commute. And the proof. All we need to show is let phi prime be the exponent of the L prime adjoint of x prime for x prime in the being strongly nilpotent in L prime. By the previous remark, x prime equals phi of x for at least one x in the strongly adjoint nilpotent elements of L. Then for arbitrary z in L, we can see how this thing acts, where phi on the exponent of adjoint of L, the L adjoint of x on z is going to be phi of z plus the bracket of x of z plus the bracket of x on the bracket of x and z over 2 and so on. Which is then going to be phi of z plus the bracket of x prime on phi of z plus the bracket of x prime on the bracket of x prime on phi of z over 2 and so on, which is just going to be the exponent of the L prime adjoint of x prime on phi of z so the diagram is going to commute as we want. I might, yeah, we're going to cut off the video here, kind of a shorter one, I'm sorry for that, but things are happening, you know how it goes. Thanks for watching.